Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am super happy to have Isabel Santos-Santos with us today. Hey, Isabel.
Hi, Frank. How's it going?
I am doing very awesome on this February 3rd of 2023. 2023 is going by so quick. We're already 1 month in. Yeah. But going very well in Phoenix. We are in our winter weather, so we get kind of cool, a little bit above freezing in the morning, but then it kind of warms up pretty nice in the afternoon. So it's all very lovely. That's why we get so many Canadian snowbirds coming down in the winter here.
Oh, that's nice.
Yeah. And how about you, Isabel? Where are you located at?
So I am in Durham. It's in the north of England. 1-2 hours away from Edinburgh for people to have a reference. And it is also quite cold now, but today it's not raining. It's a super clear sky, and yeah,
nice.
So far, nice day.
Spring is coming. Spring is coming.
Well,
slowly but
not yet in Durham, but
slowly but surely in the northern latitudes there. Yeah, it's very good. You get snow in Durham? Does it ever snow there?
Yes, but like once or twice a year, not much really.
Just a little dusting and that kind of stuff. Very cool. Very cool. And Isabel, what do you like to do for research?
Yes, so I study galaxy formation in a cosmological context, and I focus on dwarf galaxies, so the smallest galaxies that exist in the universe, because they are thought to be building blocks of the Milky Way, of larger structure like the Milky Way or the local group. And I also use them as probes for dark matter, so to study the nature of dark matter. And I do this using cosmological simulations, mainly within the cold dark matter model. And yeah, I've touched a lot of topics with dwarf galaxies. I guess I could say a few of them. The cusp core problem, which is very popular, the diversity of dwarf galaxy rotation curves, the faint end of the luminosity function, and the planes of satellites problem, which is what I'm going to talk about today, and was the main project of my PhD.
Cool. When was your PhD?
My PhD, I finished my PhD in December of 2018.
Very good.
So
very
a few
cool.
years ago now.
Awesome. And that is going to bring us to this very awesome APJ article. It's open access, people. You can go get a copy for free. Planes of satellites around simulated disk galaxies 2. Time persistent planes of kinematically coherent satellites in ΛCDM. And Isabel, take us away.
Okay, thank you. So I'm just going to start explaining a little bit the context around this paper. So this paper was part of my PhD project, as I was saying before, where we studied the planes of satellites problem in a very comprehensive way. So there was a first paper where we looked at the observational data, and then we used the method there that then we applied to simulations in a second paper, and this is the third. So I just wanted to say that to begin with, because I also wanted to give a shout out to my co-authors. So this was a long project. As you can see, there's a lot of people there. My thesis director was Rosa Dominguez, and then there's a lot of people that were involved in my thesis that ran the simulations that I'm going to talk about, that provided some tools that I used to analyze the simulation. So thank you to all my co-authors for their contributions.
Good shout out.
So the motivation for this project, the planes of satellites problem in general comes from the fact that we observe that most of the Milky Way satellites are organized like in a planar structure. And recently with Gaia, it has been possible to measure proper motions for these satellites. And what they found was that there was a high fraction of these satellites that seemed to be orbiting within this plane that they define in space. And so there's been work that has looked at this in large volume cosmological simulations, and they find that it's that cases like this, like the Milky Way one, where the satellites are so spatially and kinematically organized, are statistically rare. And so there has been some part of the community that has raised this as a important problem for ΛCDM, one of these so-called small-scale problems for ΛCDM.
Good.
So as I was saying before, there was a first paper where we looked at the data, a second paper where we applied those same methods that we had applied to the data to simulations. And in that work, what we did in the second work that I'm talking about, we identified planes of satellites using only positional data. So we just looked at the simulations. Also, I should say, sorry, I should have said this before. We're analyzing two Milky Way-like disk galaxies simulated in ΛCDM. These are hydro simulations. So our approach to the problem has been that of studying a couple of systems in detail, instead of looking at large volume simulations and looking at statistics and how frequent things can be. We were looking at, in detail. And so in this paper that went before the one that I'm going to talk about today, we searched for which were the best planes that you could find around these in satellites around these Milky Ways, no? So which were the thinnest spatial planar structures of dwarfs. And what we found, and other authors had found as well before, was that all these planes were, yes, very thin, but consisted of satellites that in general were not co-orbiting. So these structures were transient. So if you found a plane at a given moment in the simulation and you followed those satellites at a posterior time, what you find was that some of them would have been lost to the plane because they weren't orbiting within that structure, right?
Okay.
So,
okay. I'm with you.
So in this paper, we wanted to go a step further and now use not only the positional data, but also the velocity data. Because of course, in the simulations, we have everything, no?
Right.
So the idea was to see if we could find a subset of satellites in our systems that had coherent kinematics. So that they orbit within the plane that they define in space. And if we could find them, then what were the characteristics of this group of satellites?
Right.
What were the characteristics of the planes that they define? And then ultimately, find some hints towards what's their origin, how did they even happen?
Right.
Yeah. So, so as I was saying, the main point of this approach in this paper was to study the position and velocity, which means if you put both together, the orbital angular momentum. So
good.
R times V. So we could go to figure 1 if you don't mind scrolling.
Sure. Let's take a look at figure 1. We got some of the stuff about the simulations there. And figure 1, J orb.
Yeah, so about the simulations, I think I can just summarize with what I said. These are two massive halos that have a very nice disk, an extended disk, and both simulations have around 35 satellites around them.
Right.
But they're very different. They use different initial conditions, different ways of solving the gravity, and different feedback. So we think that because of these differences, yes, Aquarius C alpha and PDVA 504. Thank you for pointing that out. Because they're so different, it allows us to have results that are independent of the modeling, that come from aspects that are more fundamental to cosmology and to galaxy formation than modeling details.
Definitely. Okay.
So in figure 1.
Okay.
Yes. We can see what I'm plotting there is the angular components of the orbital angular momentum vector of each satellite of one of the systems as a function of time. So how the vector that is perpendicular to the orbital plane of the satellite, how it evolves with time. And I separate the satellites in two groups. So on the left, what we can see is that if you just look at the upper panel is theta and the lower panel is phi. So these are the angular components with respect to a reference system that is kept fixed with time. And what we can see that the lines are very stable, are straight, right? And both angular components. So this is telling us that these satellites have orbital angular momentum vectors that are that remain constant in time, that their direction doesn't change much in time.
Yep. Very good.
The gray line, the vertical gray line, that is virialization time. So the time at which we consider the growth of the halo has decoupled from expansion.
Okay.
And when we would consider that, that the satellites are bound to that Milky Way halo. And what we can see is that the lines for this orbital angular momentum vectors are stable even before that time. So virialization time doesn't seem to be an important moment in time, doesn't affect the cases for which angular momentum we say is conserved.
Right.
So yes, this conservation happens since early times. And then on the right, I separated other satellites, the rest of the satellites actually, the system, where we can see that the lines fluctuate much more. It's the orbital angular momentum vectors are noisier. And this plot was generally just to show that in a satellite population, in a satellite system, you have some that have very well conserved orbital angular momentum. We also call them orbital poles. So I may say that along the talk. While there are other satellites that don't conserve angular momentum. So yeah, angular momentum is not something, conservation of angular momentum is not something that we can take for granted that happens always. And it makes sense, no? Because the gravitational fields that these satellites are feeling change with time. We have mass flows into the halo, accretion of mass onto the disk, then can be interactions between satellites, right?
Right.
So some satellites are affected by that and don't conserve their angular momentum, while others can conserve it for long periods of time. If we can go to figure 2 now, to the first upper panel.
Very good, I'm with you. Very good. Ooh, pretty. Okay.
So this is an height of sky diagram. So here we're seeing essentially the same data that I was showing before in angular components, but now it's projected on the sky. So theta and phi are now projected on the sky.
Nice.
Just to explain a bit clearer. So here, each symbol and color represents a different satellite.
Right.
And there's a label for each satellite at one of the points. So each point corresponds to a different time step of the simulation.
Okay.
I'm looking at the projection of the orbital pole from virialization time to redshift 0. And each point corresponds to one of those time steps. And then the label is at the redshift 0 moment, so you can have a reference.
Very good. Thank you for that. Very good. Okay.
And so the same idea that I was explaining before, the idea that there are some satellites that have orbital poles that are conserved in time and others that don't, is very clearly seen here. So the cases that have these tracks that are super long that span a very large angular distance on the sphere, those are clearly cases for which angular momentum is not conserved.
Yes.
While the tracks that are more like concentrated, like that case, those are objects for which satellites for which the angular momentum is conserved in that period of time.
Okay. Very nice. I like
so this. Stay there for a second.
Okay.
There is another aspect that we can clearly see with this plot here, and it's that not only there are objects that have conserved orbital poles, but also we can find that there's an accumulation of objects like in the same area of the diagram. So for example, that group there, or on the left, there's another group.
Yeah, very good.
So there is a clustering. There's clustering in this orbital angular momentum space, right? So there are satellites that not only conserve their angular momentum, but their orbital poles are pointing in this similar direction. And so what this is telling us is that there is a subset of satellites that have a common orbital plane, and that this orbital plane is maintained in time. So the aim of this paper, as I was saying, was to see if we could find groups of satellites that were kinematically coherent and formed planes. No? So we are going to use the fact that we find clustering and conservation of orbital angular momentum to identify, to define these subsets of satellites with coherent kinematics. And then of course, in the rest of the paper, we study what's the plane that they define, sorry, and the characteristics of that. So the method by which we identified these groups, which we called KPP for kinematically persistent planes.
KPP.
KPP satellites, was the following. I won't go into much detail, but just to, explain a little bit.
Set it up.
So we took, so the method consisted in finding an axis of maximum satellite co-rotation. So this is, is there any direction in the sky around which we find a maximum number of orbital poles of different satellites? So essentially, if we look at this diagram here, what we did was we stacked all the data that you are seeing here, which is orbital poles at different times for all the satellites. And then we scanned the sphere and searched for the direction that enclosed the maximum number of orbital poles within a certain aperture.
Okay.
And I mean, there's details to that, of course, but the outcome of that is this axis that we found. No? And for example, for this case that I'm showing here, which is the Aquarius C simulation, that X, that magenta X, that is the axis that we found. Okay. So what is important here as well is that we're not differentiating between satellites that rotate. So while sharing a common orbital plane, you could have satellites orbiting in one sense or in the other. So we are not differentiating between that. We only care about them sharing the same orbital plane. Right. So in that sense, these the axis, this X, there are two X's, right? But that's the same orbital plane. It's just the vector that goes up and down, right? So it would, the circles are enclosing objects, satellites that are orbiting in the same plane, but the ones on the right are orbiting in one sense, and the ones on the bottom left are orbiting in the other. Okay, all right. But if we go to panels B and C below. Yes. So if we, as I was saying, we don't differentiate between rotation in one sense or the other, and we could fold that diagram that I was showing you before, right? And we would only have one axis and one circle, and all the satellites that rotate in that circle would overlap. And that's what we are seeing in the left-hand diagram. So on the left, we can see all the satellites that are rotating around this axis. Yes. That were before separate by their rotation, but now we're plotting them together. Right, 345, for example, 345 right here. Yes, okay, I'm with you. Yep. Exactly. And okay. More quantitatively, the way in which we decided which ones were in the KPP group was by defining that they had to have more than 50% of their time steps, of their points, within these co-orbiting circles. Okay. So that's the way we quantified it. Okay. Of course, there are objects that are completely inside the circle, so 100% of their time steps are co-orbiting, we would say, around that axis. And then there's some that have a lower fraction of their time steps co-orbiting. So this allows us to have like a ranking, right, of satellites according to how probable, how well kinematically associated to that axis they are. Right. But as I was saying, we kept those with, for this kinematic group, those with more than 50% of the outputs. Okay. Okay. So now we have defined a group of KPP satellites. And then we're interested in seeing if they define a plane in space. And if it persists in time and what this plane looks like, etc. Yep. So that's what we're going to do next. But before, I should also say something about the other simulation. For the other simulation, we did the same method. We found, we plotted the tracks of the orbital poles and night of projection, and we identified axis. In that case, what we found was, instead of one main cluster, we found two somewhat smaller clusters or groups of satellites with conserved orbital angular momentum in similar directions. And all our analysis is done for both those groups as well. So we'll see that in the next figures. So if we can go to figure 4.
Figure 4. Okay, figure 4. Boom, and time evolution planes. Okay.
So these 3 figures show the 3 planes associated to each of these 3 kinematic satellite groups or KPPs. And each panel is a characteristic of the plane. So the way in which we and everyone in general fits planes to these groups is by using the tensor of inertia method. So this essentially is it fits an ellipsoid to your set of points.
Okay.
And so in an ellipsoid, you have a short, an intermediate, and a long axis.
ABC.
And so by comparing those axes, you can say how flattened the distribution is. Yes, exactly. Or how oblate or like pancake-like or filamentary or whatever. So C over A, that is the short over long axis ratio, and that tells you how thin it is.
Okay.
And then B over A is the intermediate over long, and that tells you how pancake-like. So if it's large, then it's extended in that dimension. And so if we are thinking of what would be a good quality plane, like a thin plane, that would be something with a low C over A and a high B over A.
Yes.
So for, let's ignore the fact that there are these 3 lines in each case, the 3 shades of colors in each case. But if we just look at the trends overall, what we see if we focus on C over A and B over A is that for the 3 cases, the planes have low C over A and in general, high B over A.
Yeah.
So
the 11, 12, 13 year or the time slices?
The 11, 12, 13 are the number of satellites that we consider in the plane. So for the Aquarius C Alpha simulation, we found that the KPP group had 13 satellites according to this criteria of having more than 50% of the output. So that group was 13 satellites.
Okay.
In PDIVA, we found 2 groups, and one had 10 satellites and the other one 7.
Okay.
And what we're doing here by with the different shades is what would happen if we fit the plane to the sample, but without the last one. Okay. So instead of 13, for example, 12, and instead of 12, 11.
Gotcha.
Because we wanted to prove that the way in which we had selected our group was a robust criterion, no? So it's not like, okay, if I'm not taking one of the satellites, would the plane change much?
Right.
No, what we're showing is that the results are essentially the same.
Good. Okay, I'm with you.
So we found that yes, there are planes. There are planes for the whole period analyzed from virialization time to redshift 0.
Yeah.
There are some moments at which the quality is better. So the C over A is very low and the B over A is very high. But in general, it works. Yeah, so for example, in the middle, so for PDIVA 1, it is true that B over A becomes not too large, around 0.5 at some period. That's still planar, but it's less oblate, let's say, compared to the plane of Aquarius, for example, on the left, or the green one on the right. Yeah.
Right.
But in general, yes, these are planar structures for the whole period. The third panel is the minimum distance to the center of the central galaxy. So we are not forcing our planes to pass through the center of the galaxy. We're just fitting the planes to the satellite positions. And sometimes it occurs that there are fluctuations in this distance. So one would expect that if the satellite system is bound to the central galaxy, then they would always be orbiting with the center centered on the main galaxy.
Makes sense.
But as you can see here, there are fluctuations in that panel. And what we found was that those fluctuations, which are not very big, but they exist, happened at moments at which the satellite population was heavily lopsided. So all the satellites of the plane were, let's say, on one of the sides of the galaxy. So then if you fit a plane to that, it's not going through the center, right? So fluctuations, but ones that we understand and that we expect.
Mm-hmm.
Then the fourth panel is just telling us what's the fraction out of the total that this KPP group represents.
Okay.
And for Aquarius, it's 13 satellites. And as I was saying, we have on average 30 or 35.
Yeah.
But so it's something like 40%. But of course, this fraction can change in time because some of the satellites of the system end up merging with the central galaxy. So the total number decreases with time.
Okay.
The satellites, these KPP satellites, those don't merge. We chose them to be, things that would survive.
By death, right? Uh-huh.
Then the bottom panels, those are showing the orientation of these planes. So yes, the N sub KPP, that is the normal vector to this plane. And again, it's divided in the angular components in theta and phi. And again, for the three planes, what we find is that the normal vector is very, very stable. It doesn't change much. It's a bit difficult to see in angular components. Perhaps if we projected it on the sphere, we would see. But again, we would see that like what we were seeing with the tracks, they don't span, they don't move around on the sphere, right?
Stabilized.
Exactly. And then the bottom panel is very interesting. The bottom panels are showing the angle formed by this normal vector to the plane with the spin vector of the disk.
Yes. Yeah.
And what was interesting was that we found that most of the time, the two vectors were perpendicular to each other.
Yep.
Yeah. So the angle they form is close to 90 or highish, let's say around 80 most of the time.
Yeah.
So this is interesting just by itself because it happens in all three cases. For the third plane in green, after 10, 11 gig years, it goes somewhere. Yes. But it's interesting as well because in the Milky Way, the plane of satellites is also polar to the disk.
Okay,
so
that's good enough. Okay.
There may be a reason why that is the case, maybe not, but it looks like, at least in that sense, these findings are consistent with our observations for the Milky Way.
That's always good.
So we found that these KPP satellites, they define planes. These planes have some common characteristics. They persist in time, which is very interesting. So we asked ourselves if these satellites were special in any way, if they were different to the rest of satellites of the system.
Okay.
So I think the next figure is about that.
Figure 5. Oh yeah. Oh yeah. Spaghetti.
So here the idea was to study if there was some property that would distinguish the KPP satellites from the rest, and could give us some insight into why they have that special behavior and they're different. And so we studied a few things. This plot here is showing in the upper panels the magnitude of the specific orbital angular momentum.
Okay.
And on the left, it's for the Aquarius C KPP, and on the right for the two planes in PDIVA. And then each individual line is showing the evolution of this magnitude of the angular momentum for each satellite. The colored ones are the KPP satellites, and the gray ones are the rest.
Gotcha.
And
okay,
we computed medians, which are the thick ones. And so, in general, what we found was that if a satellite belonged to a KPP, then on average, they have larger specific orbital angular momentum. And the same for it, we found the same result in both simulations.
Yeah.
And then in the bottom panels, it's the angle between the orbital angular momentum and the disk again. And as we were seeing with the plane itself, KPP satellites orbit more polar to the disk, more perpendicularly to the disk than the rest of satellites.
Yes.
And then we also looked at other aspects like the pericentric distance of satellites in one sample and in the other. And we found that KPP satellites showed on average larger pericentric distances than the rest.
Okay.
So these three Okay, and then this was computed with statistical tests called Molgorov-Smirnov tests. So these differences are telling us that yes, the populations are statistically different. So these three characteristics, the fact that they have higher specific angular momentum, higher larger pericentric distances, and they orbit more perpendicular to the disk, kind of suggests that these satellites are less affected by secular evolution from the disk. So less affected by tidal effects from the disk and interactions with other satellites even. So the fact that they have a larger magnitude of the orbital angular momentum vector implies that they would have longer orbital periods as well. So they would reach further out distances for a longer period of time. So they spend less time close to the disk and less time affected by those forces.
Right.
At the same time, larger pericentric distances, same idea, right? Less affected.
Very cool.
And
very nice.
Orbital orbits that are perpendicular to the disk also feel less tidal forces from the disk.
Mm-hmm.
Yeah. Mm-hmm. So this would explain why these satellites were able to conserve angular momentum for the whole period. No, nothing has disturbed them, let's say.
Right. Very cool. Nice.
Okay, so the next figure.
Kinematically, late subsatellites and capture processes.
Yeah, so this part here, this section was about studying a very interesting event that happened in one of the simulations.
Okay.
And it's the fact that this Aquarius C simulation, we find that it has an LMC-like dwarf group at infall at redshift 0. Okay. So there's been some literature studying the planes of satellites problem, where they found that they were studying simulations, and they found that when they looked at Milky Way halos that had an LMC, a massive dwarf at first infall today, with its sub-satellite system, if their simulation included that, then they were able to find more and thinner planes that were more kinematically coherent.
Interesting.
In general, than in the halos where they did not have one. So there's some discussion about what's the role of the LMC in our observed Milky Way plane. No, if it's the Milky Way driving all our observation. Sorry, it's the LMC driving all the plane, or no. So in Aquarius C, we have an LMC. So we studied this.
Okay.
So we looked at how this LMC dwarf, which had its own satellite system, it had 6 satellites around it, how it impacted the KPP that we had identified in Aquarius at redshift 0. So on the left, I'm showing again the specific orbital angular momentum vector, magnitude, and then the vector itself in theta and phi angular components in the middle and bottom panels.
Right.
And this is for the satellites of this LMC, so sub-satellites of the system, before the whole dwarf system is captured by the host galaxy. So when we're looking in the reference frame centered on the massive dwarf, centered on this LMC dwarf, and at times earlier than redshift 0 when the thing is captured.
Right.
And so what we found is that the subsatellites have a stable magnitude of their angular momentum, and their orbital poles are very stable as well. So straight, stable lines.
Right.
All this up to around 12 gigayears in the age of the universe, which I've marked with that arrow.
Yes.
That is the moment at which the LMC group is captured by the host galaxy, and we can start to see that there's a transfer of angular momentum. So the sub-satellites will start to unbound from the LMC and bound to the host galaxy.
Nice.
If we look at the ITOF diagram below, this is showing the same thing, the projection of the orbital poles of these sub-satellites before they are captured. And it was super interesting that we found that 5 out of the 6 satellites form a KPP themselves around the other.
Okay.
So
any KPP.
A KPP. They have clustered and conserved angular momentum orbital poles, with 4 of them rotating in one sense and 1 in the other, which is the orange one on the other side.
Yes, exactly.
And then what happens after, when the group is falls into the main Aquarius C halo? That's what we can see in the right panels above. Yeah. So it says reference frame centered on host galaxy.
Okay.
So of course, before 12 gigayears, before it's captured, the lines are super noisy because the sub-satellites are not associated to the host. They are in a different reference frame.
Right.
But after 12 gigayears, when the group gets bound to the host galaxy, we can see that the lines start to stabilize again. They become stable and straight. So the satellites are now bound to the main galaxy. So we can see the transfer of angular momentum in one group being captured by the other. And what we found is that at redshift 0, 3 of the new 7 satellites, so LMC plus its 6 satellites, 3 of those, including the LMC itself, become part of the original KPP that we had found in Aquarius.
Yeah, very good.
So they joined the group, and some of them, 3 of them, are part of this subset of KPP satellites. So our conclusion was that, okay, you don't need an LMC with an LMC group to have a kinematic plane, but it can enhance your structure and it can add on to the number of satellites rotating in one sense versus the other. Right.
Very nice. That makes total sense. Cool.
And yeah, and I guess the next figure and last figure. So this figure is not very beautiful, but it has a point to it. So
that's good.
So here, this section was about comparing so as I was saying before, there was a previous paper to this one where we studied the same simulations, but from using only position information.
Right.
So we were looking for the best planes of satellites that you can find in position space.
Okay.
And here we're using the whole information. So we have kinematic planes. Okay. So we compared both, no?
Yes.
In that paper, we defined the best positional planes as the thinnest planes that you could find at a given time step, including a fixed fraction of the number of satellites. So that's what it says there, FSAT, 50%, 70%.
70 and 90. Gotcha.
So here, what I'm showing in the upper panel is the angle formed by the normal to the positional planes and the spin of the disk galaxy. This is for Aquarius C as well. And of course, depending on what kind of positional plane you're looking at, if you're looking at one for a fixed fraction of 50%, it's going to be more noisy, your results, with time than one for 90%, because there are more combinations of 50% of satellites than there are of 90% of satellites, right? If I look at, if I have this up. And the thinnest plane that you can find at a given moment will be made of some satellites, but then at the next moment, because I'm only looking at positions, I may choose a totally different sample of satellites, right? And so the normal vector to these best positional planes is expected to change with time.
Right.
And of course, it's going to fluctuate more for 50% than 90. What we found was that if you look at the thick line, the 9 for 90%, it actually doesn't fluctuate much. So it's very stable, and it coincides with the same plot for our kinematic plane here, right?
Yes.
So the positional plane with 90%, the best that you can find at a given time, and our kinematic plane of this paper are following the same angles. So this already hints to the fact that they can be the same structure.
Yes.
But then on the bottom panel, we're directly comparing the alignment between the two. So this is the angle between the normal vector to the KPP and the normal vector to the positional plane. And again, let's focus on the 90% line, on the thick one. What we can see is that the alignment is better than 15 degrees for almost the entire period analyzed, right? There's only these moments around 10 gigayears, and then at the very end where the alignment is a bit worse. But other than that, the two structures are essentially the same configuration in 3D space, right? So this has implications to how we understand our this planes of satellites problem. So this would mean that the positional planes that people are finding in observations without velocity data, right? They're just observing systems, they're finding satellites, they are seeing that they are aligned. These alignments could actually be a signature of an actual kinematic plane in the background, no? So the conclusion is that the kinematic planes, these KPPs, work as skeletons to these positional alignments that we can find. And these the positional alignments would not be just patterns that we think we're finding, but actually the manifestation, the reflection of an underlying group of satellites that is kinematic, and etc.
Gotcha.
So these positional planes that we thought were transient would actually be long-lasting structures. It's just that they would be unstable because they would consist of a backbone, which would be the KPPs. Right. But then as well, at each moment in time, you can find other satellites that by coincidence are in positions located over the same plane. Okay. So yeah, that's the idea that we wanted to put forward with this comparison. Nice. Very good. And that's basically all the main ideas of this paper.
And if you want some really nitty-gritty details on how KPP was defined, you can check out the appendix.
Yes. So in the appendix, we include more detailed explanation of how our method works, and then an alternative method that we also applied and finding the same results. So just to prove that our method was robust, and then some details of the analysis to PDEVA. Of course, we found the same trends in both simulations, but we weren't going to repeat all the figures. So that's why I focused today on only explaining.
Very good. Very nice. Very nice. Lovely. Very nice. And Isabel, thank you so much for walking us through your very lovely article. Appreciate it.
Thank you. Thank you so much for inviting me and giving me the opportunity.
Sure. You touched on it a couple of times, or you hinted at it a couple of times as you went through, walk us through your paper. And so let me ask, where do you think we go over the next, let's say, 2 to 5 years on this topic? Are there additional large-scale simulations to analyze? Are there other subgroups to analyze? Maybe there's some observational work to be done? So just kind of next steps, where do you think we go over the next couple of years? Will there be a paper 3 in this series?
Yes.
Okay.
That's what I would like to say. So our approach is to keep on studying in detail these two simulations, right? So in this paper, we found that they exist in first place, that you can find them in ΛCDM simulations, that they have common characteristics, and that they seem to gain this common dynamics. The satellites seem to gain this coherent kinematics at very high redshift. But how? No, the question is, how do they gain this common dynamics? No, when does the clustering of the satellites set in? Good. And why? Okay. And so there's a PhD student in Universidad Autónoma de Madrid, where I did my PhD, that is following up with the project that I just presented, and he's studying precisely this question: no, how do the KPPs appear? What happened at high redshift for them to gain a common kinematics and persistent time? No? Yes. And it's very, very interesting work. So in this project, what he's doing is he's relating the orbital angular momentum of the satellites to how the cosmic web evolved, especially at early times. So the cosmic web is this is the large scale structure, right? It's the mass at larger scales, no? And what we know that it is very anisotropic, so that it's distributed in what people call sheets, filaments, voids, halos, or knots, or whatever. And so with his work, what he's finding is that as the mass flows at very high redshift, so the mass that is around, that is going to eventually become this halo with its satellites and all that, if we followed that mass from where it comes from,
yes,
we would find that as it flows, it flattens. It starts flattening with a preferred direction of flattening, or collapse, what people say. That is fixed at very, very early times. That imposes a direction in which mass flows, and mass collapses to a sheet, a planar structure. And so the motion of the satellites becomes confined to that planar structure as well. And then there's nothing that really disturbs the dynamics of these satellites, and they can maintain the conservation of their orbital momentum, maintain that orbital plane until later times, which is what I showed in the conservation at later times is what I showed in this paper. And then he's showing where it came from.
Cool.
So I think that's really interesting. And yeah, hopefully it will be out soon, the next months or whatever.
Very nice. Very cool.
Yeah.
Well, I look forward to seeing that one. In fact, I'm looking forward to seeing this field evolve in the next couple of years, and we can figure out where these
and observationally we do expect a lot of new being able to observe more dwarf systems and seeing if these alignments are really ubiquitous, if they're everywhere or not really. Also, if we could have more velocity data for satellites, it would be able to constrain better. Yeah.
Well, we've got a whole number of new telescopes coming up here over the next couple of years. So it'll be really cool to see this go forward. Very nice. Very nice. Isabel, thank you so much once again for walking us through your very lovely article and projecting the future of this topic.
Thank you. Thank you so much. It was very fun.
And that'll do, everyone. And I hope this made your astronomy day just a little bit better, and we will see you on the next one. Bye-bye.
Bye.